Tonight, I want you to picture a top spinning on a wooden floor. A child started it. Before that, the top was still. There's always a moment, in everyday life, when something stationary becomes something rotating. Somebody pushed it. That is how spin works in our world. Now take that idea and try to apply it to the universe. It does not fit. Nowhere in physics, at any scale, has anyone ever found the moment something started spinning from rest. You will hear how a cloud of gas hands its rotation to its children before it dies. You will meet the exception that proves the rule, a planet on its side, a galaxy spinning backwards. You will encounter the number that broke the simple version of this story in 1992 and has never quite been put back together. We begin. Right now, somewhere in the room you are in, a small object is sitting still. A coffee mug, a book, the lamp on your bedside table. You would not say any of these things are moving. They are sitting there, quiet, stationary. Inside each of them, nothing is still. Every atom in that mug is built from electrons, protons, and neutrons. Each one of those particles carries a property physicists call spin. It is not a metaphor. It is a real measurable quantity, with real units, that behaves mathematically like angular momentum, even though it is not a tiny ball physically turning on an axis. Every electron in your hand has it. Every electron in the mug has it. Every electron in the air between you and the mug has it. There are roughly 10,000 quintillion atoms in a single drop of water, and inside each one, particles are carrying this small, built-in piece of rotation. You will never see it directly. The world we live in is too large and too warm for the strangeness of quantum spin to be visible. But every atom in the mug is humming with it. Now lift your eyes. The lamp is sitting on the table, but the table is sitting on a floor, and the floor is part of a building, and the building is bolted to a planet that is spinning on its axis at roughly 1,000 miles an hour at the equator. The planet is curving around a star at 67,000 miles an hour. The star is sweeping around the center of a galaxy at 500,000 miles an hour. The galaxy itself is drifting through a larger structure, and that larger structure is drifting too. You are sitting in a chair that feels still. You are spinning in 7 different ways at once, and you cannot feel any of it. This is the strange situation we are in. At every scale we can study, from particles to planets to galaxies, rotation keeps appearing. Not everywhere in the same way. Not always with the same meaning. Some objects rotate slowly. Some rotate so fast they would tear themselves apart if they were made of anything weaker than what they are made of. But often enough, almost everywhere we point our instruments, we find spin. Stillness, the most ordinary thing in our daily life, begins to look like the stranger idea. And the question that hides underneath this fact is the one most people never think to ask. Why? Why is rotation everywhere? Why is stillness, the most ordinary thing in our daily life, completely absent from the cosmos at every scale we have ever measured? What is doing this? The answer is stranger than you would expect. There's no answer in the way you would expect one. Spin, in the universe, was never started. Spin was inherited. When something starts spinning in your kitchen, it is because a force did the work. The blender turns because an electric motor pushes it. The top turns because a child pulls a string. The fan turns because the wall socket sends current to the coils. Every rotation in your house has a cause, and the cause is recent, and the cause involves something pushing on something else. Physics has a name for what a push gives to an object. It is called angular momentum. Angular momentum is the technical term for the amount of rotation a thing has. A bowling ball rolling slowly down a lane has a small amount. A spinning ice skater has a moderate amount. A neutron star, which we will meet in a few minutes, has an amount so large the numbers look made up. Here is the law that governs all of it. In an isolated system, the total angular momentum cannot simply appear from nowhere. Local spin can be transferred from one object to another. It can be redirected. It can be paired with an opposite spin somewhere else. But the total accounting always has to balance. This is one of the deepest rules in physics, and it has never been seen to break. Not in any experiment. Not at any scale. Not under any condition. The short answer to why everything keeps spinning is that conservation law. The deeper answer, which we will get to, is a kind of symmetry hidden inside the laws of physics, a symmetry first explained by a mathematician named Emmy Noether in 1918. And the deepest answer of all, which is still being argued over, is that some theories now suggest space itself may be built from rotation at the smallest scales. We will walk to all three of those answers, slowly, before the night is over. For now, hold the simple version. Total angular momentum has to balance. Now read that again, and feel what it implies. If new angular momentum cannot just appear inside a system, then most of spin you see around you was already there. Somewhere, in some form, before the thing that is now spinning existed. The Earth is rotating. Where did the rotation come from? Not from Earth itself. Earth got its spin from the cloud of gas and dust that collapsed to form the solar system 4.5 billion years ago. That cloud was already rotating. Where did the cloud get its rotation? From the larger region of the galaxy it was part of. Where did that region get its rotation? From the larger structure of matter that fed into it during the early universe. And so on. Backwards. All the way back. There's no point in this chain where rotation was added. Every link inherits its spin from the link before it. Every cloud passes its rotation to the smaller clouds it breaks into. Every galaxy passes its rotation to the stars and planets it builds. Every star passes its rotation to whatever it leaves behind when it dies. Spin is a hand-me-down. It does not get bought. It only gets passed on. Which means somewhere very early, in the first moments after the Big Bang, the universe already had rotation in it. Nobody put it there. Nobody can fully explain why it was there. But it was. And every spinning thing you have ever seen, including you, including the atoms in your hand, including the Earth, the Sun, the galaxy, is carrying a small piece of that original gift. The question of why the universe spins is really the question of where that first inheritance came from. And on that question, we have several theories, no consensus, and a quiet sense among physicists that we may never know. To understand how deep this hand-me-down goes, we have to go back to a small experiment in Germany that nobody at the time understood properly. The year was 1922. The place was Frankfurt. Two physicists, Otto Stern and Stern-Gerlach, had set up something that looked, at first glance, like a piece of kitchen equipment. They had an oven. Inside the oven, they put a small amount of silver. They heated it until the silver evaporated into a thin beam of atoms, drifting through the air. Then they aimed that beam through a carefully shaped magnetic field, and let it land on a glass plate at the other end. They were trying to settle a question. At the time, a Danish physicist named Niels Bohr had proposed a model of the atom in which electrons followed very specific paths. According to Bohr's model, an atom flying through the right kind of magnetic field should land on the plate in a clean, simple pattern. Stern and Gerlach were trying to prove Bohr was right. They were not trying to discover anything new. They were trying to confirm a theory that already existed. When they pulled the plate out of the apparatus, they saw something nobody expected. Two spots, with a clear gap between them. Not a smear. Not a single spot. Two. The result confirmed Bohr's prediction. Except Bohr's reasoning turned out to be wrong. Let me say that more carefully, because it is one of the strangest things in the history of physics. Stern and Gerlach got the right answer for the wrong reason. Their two spots were real. The pattern they saw on the glass was correct, but the explanation underneath it, the model Bohr had given them, did not actually fit. Something else was producing the two spots. Something nobody had named yet. It took 3 more years for anyone to figure out what. In 1925, two young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, working at the University of Leiden, proposed that the electron itself was rotating, not orbiting an atom, the way the planets orbit the sun spinning, like a tiny ball turning on its own axis. They were so nervous about what their advisor would say about this idea that they tried to take the paper back after submitting it. He told them no. The paper was already in the mail. It was published. And it was right. The two spots Stern and Gerlach had seen were caused by the electron's own spin pointing in two opposite directions, up or down, nothing in between. Here is what made this discovery so unsettling. The electron is not really a small ball. If you tried to model it as a tiny rotating sphere, the math would require parts of it to move faster than the speed of light, which is not allowed. The electron spin is not a literal rotation in the everyday sense. It is a property the electron has, a built-in piece of angular momentum, that behaves exactly as if it were rotating, even though nothing inside the electron is actually turning. And this is true of every electron, every proton, every neutron. They all carry spin. They cannot get rid of it. They cannot give it up. Every fundamental particle in your body is born with a fixed amount of spin, and it dies with that same amount. The spin was never started. The spin was always there. That is the bedrock. Every other rotation in the universe sits on top of this foundation. Now climb up one level. From the spin of a single electron, walk outward to the spin of an entire planet. The mechanism that connects them is the same mechanism that is moving the moon away from us right now. About 4.5 billion years ago, in a quiet corner of the Milky Way, a giant cloud of gas and dust began to fall in on itself. It had been drifting through the galaxy for a long time. It was made mostly of hydrogen, with smaller amounts of helium, and traces of heavier elements that had been scattered into the galaxy by the deaths of older stars. This cloud was rotating. Slowly, almost imperceptibly. The rotation came from the larger arm of the galaxy it was part of, which had been rotating since the Milky Way first formed, which carried its rotation from the larger structure of matter in the early universe. Then gravity started to pull the cloud inward. Here is where one of the most beautiful tricks in physics shows up. When a rotating object pulls itself in, it speeds up. You have seen this with ice skaters. A skater spinning slowly, with her arms out. She pulls her arms in. She accelerates. She is now spinning fast. She did not push off the ice. She did not gain any new rotation. She just took the rotation she already had and concentrated it into a smaller space. That is conservation of angular momentum. Squeeze something rotating into a smaller volume. It spins faster. Stretch it out. It slows down. The amount stays the same. The cloud that became our solar system did exactly this. As it collapsed under gravity, the slow drift it had picked up from the galaxy turned into a fast spin. The spin flattened the cloud into a disk. The disk gathered most of its mass into a hot center, which became the sun. The leftover material in the disk clumped into smaller objects, which became the planets, all of them rotating, all of them carrying the same direction of spin as the original cloud. That is why the sun rotates in roughly the same direction as the planets orbit it. That is why most of the planets rotate in the same direction as their orbits. They all came from the same spinning disk, and they all kept their share of the disk's angular momentum. There are exceptions. We will get to those. But first, look at what is happening between Earth and the Moon right now. Right now, as you listen to this, the Moon is moving away from Earth at about 3.8 centimeters per year. That is roughly the speed your fingernails grow. We know this because in the late 1960s and early 1970s, astronauts left small mirrors on the surface of the Moon. 5 sets of them, the Apollo missions, and a Soviet rover called Lunokhod. Today, observatories on Earth still bounce laser pulses off those mirrors. The light goes up. It hits the mirror. It comes back. By measuring the exact time the round trip takes, astronomers can track the Moon's distance to within a few millimeters. And every year, the round trip takes a tiny bit longer. The Moon is leaving. The reason is angular momentum. Earth's spin is dragging on the oceans. The oceans bulge slightly toward the Moon, and slightly away on the opposite side. But Earth rotates faster than the Moon orbits, so the bulge gets dragged ahead of the Moon's position. The bulge is mass. The mass is gravity. The gravity pulls the Moon slightly forward in its orbit. Pulling the Moon forward speeds up its orbit. A faster orbit is a higher orbit. Higher orbit means farther from Earth. Meanwhile, the same drag is slowing Earth's rotation. Atomic clocks have measured this. Earth's day is getting longer by about 1.7 milliseconds every century. A few 100 million years ago, a day on Earth was 22 hours, not 24. Earth is losing rotation. The Moon is gaining orbit. The total angular momentum of the system is the same number it has always been. Nothing is being created. Nothing is being destroyed. Rotation is moving from one body to the other, the way a hand-me-down sweater moves from an older sibling to a younger one. And here's the part that is easy to miss. This same trade is happening at every scale. Galaxies trading rotation with their satellite galaxies. Stars trading rotation with their planets. Planets trading rotation with their moons. particles trading rotation with their nearest neighbors. The whole universe is one slow, ongoing exchange. Step away from Earth for a moment and look at the sun. The sun, when you look at it from a distance, seems like a simple thing. A bright sphere, a ball of plasma that sits at the center of our solar system and rotates the way you would expect a ball to rotate. But the sun is not solid. It is a fluid, made almost entirely of hydrogen and helium hot enough to have lost their electrons. And because it is a fluid, it does not have to rotate the way a solid ball rotates. It does not. If you tracked a feature on the sun's equator, a sunspot for example, and watched it disappear around the edge of the sun and reappear on the other side, you would find it takes about 25 days to come back. That is the sun's equatorial rotation period. Now do the same thing at higher latitudes. Halfway up toward the pole, the rotation slows down. By the time you get close to the poles, a single rotation takes about 35 days, 10 days longer than the equator. The sun does not have one rotation rate. It has many. Different latitudes rotate at different speeds, all at the same time. Astronomers call this differential rotation, and it is one of the most consequential facts about our star. The first person to notice this was a German Jesuit named Christoph Scheiner. In the year 1630, he was watching sunspots through one of the very early telescopes, tracking how they moved across the solar surface, and he saw that spots near the equator moved faster than spots farther up. The discovery was buried in a heavy Latin book and ignored by most of his contemporaries. It took another 2.5 centuries before the importance of the observation became clear. Today we measure the sun's rotation in two main ways. The first is the same way Scheiner did it, by tracking visible features on the surface. The second is much stranger. The sun, like a struck bell, vibrates with sound waves trapped inside it. Helioseismology, the study of those internal sound waves, lets us listen to the sun the way a doctor listens to a patient's chest. The vibrations behave differently depending on how the layers underneath are rotating. By studying the patterns, we can map the rotation of the sun's interior down to its core. What we have learned is that the differential rotation we see at the surface extends through almost the entire outer envelope of the sun, the layer where heat is carried up from the deep interior by churning columns of plasma. Below that envelope, around 70% of the way to the center, the rotation suddenly stops, varying with latitude. The deep interior of the sun rotates almost like a solid ball. There is an invisible boundary between these two regions. The boundary is called the tachocline, and it is one of the most important places in the solar system for a reason most people never consider. That boundary is where the sun's magnetic field is born. Here is the chain. The differential rotation of the outer sun shears its magnetic field, the way a stack of paper shears when you push the top sheet sideways while holding the bottom sheet still. The shearing twists the field into ropes. The ropes become unstable, rise to the surface, and emerge as sunspots, solar flares, and the great looping arcs we sometimes catch on space telescope footage. Every 11 years or so, the twisted field reaches a kind of breaking point. The sun's magnetic poles flip. North becomes south. South becomes north. And the cycle starts again. That 11-year cycle, the rhythm that drives space weather, that determines whether GPS satellites work properly, that triggers the auroras you see in northern skies, all of it traces back to one fact about the sun: different parts of it rotate at different speeds. And this differential rotation, like every other rotation we have talked about, is not new. The sun did not invent it. The sun is a fluid that inherited its rotation from the spinning disk that formed it. And the way that fluid settles into different rotation rates at different latitudes is determined by deeper physics we still do not fully understand. Recent simulations suggest that the temperature difference between the sun's poles and its equator, only about 5 degrees Kelvin, may set the upper limit on how strongly the differential rotation can be sustained. The sun, in this picture, is rotating about as differentially as it physically can. The next time you see the news mention a solar flare, or an aurora display, or a satellite glitch caused by a coronal mass ejection, think of Scheiner watching the sun in 1630, noticing that the spots near the equator moved faster than the spots near the poles. The reason any of those events happen is that the sun, like the Earth, like the galaxy, is not a single rigid spin. It is many spins braided together, all carried forward from a cloud that fell apart 4.5 billion years ago. Climb one more rung. If a planet's spin is the inherited rotation of a collapsing cloud, what happens when something much more violent collapses? What happens at the death of a star? About 28,000 light-years from Earth, in the constellation Sagittarius, there is a globular cluster called Terzan 5. A globular cluster is a tight ball of old stars, hundreds of thousands of them, packed close together. Inside Terzan 5, there's one object that is not a normal star at all. It is the remains of a star that died, then was lifted back into a strange new state by matter falling onto it from a companion. Astronomers call it PSR J1748-2446 AD. The label is a coordinate. Most of the time, they just call it the fastest pulsar. It is roughly the size of a city, about 16 kilometers across. It has the mass of nearly 2 suns compressed into that small volume. The density is so high that a single sugar cube of its material, if you could somehow bring it back to Earth, would weigh more than every human being currently alive. And it is rotating 716 times every second. Hold that for a moment. 716 complete rotations every second. Faster than the blade of a high-speed kitchen blender. Faster than anything you have ever seen rotate in your daily life. The surface of this star is moving at roughly 1/4 of the speed of light. Light, the fastest thing in the universe, would take only a fraction of a millisecond to circle this star at its equator. The star itself almost keeps up. How did it get there? Before it died, this object was a normal star, not like our sun, but in the same general family. It rotated slowly, maybe once a month, the way most stars rotate. Then it ran out of fuel. Its outer layers exploded outward in a supernova. The core was left behind, a tiny dense ball of neutrons. And as that core collapsed from a star-sized object to a city-sized object, the same trick the ice skater pulls happened again. The rotation stayed the same. The size shrank by a factor of 100,000. The spin rate had to skyrocket to keep the angular momentum constant. That is most of the explanation. But for this particular star, there is more. It has a companion. A second star orbits close enough that the neutron star pulls material off it, slowly, decade by decade. That falling material does not just add mass. It adds rotation. Every gram of gas that spirals onto the surface gives the neutron star a little more spin. Astronomers have a word for this process. They call it recycling. A neutron star, born already spinning fast, gets spun up to extreme speeds by the slow infall of a companion. The fastest pulsars in the sky are almost all in binary systems, almost all old, almost all inside dense star clusters where close encounters are common. There is a theoretical limit, around 730 rotations per second. The centrifugal force at the equator of a neutron star starts to compete with the gravity holding it together. Spin any faster and the star begins to come apart. The current record holder is sitting only 14 rotations below that ceiling. Stop. Feel that for a second. There is a city-sized object in the sky, 28,000 light-years from here, made entirely of nuclear matter, rotating just slightly slower than the speed at which it would tear itself apart. And every rotation in it can be traced back, link by link, to the slow drift of the cloud that made the original star, and the slow drift of the galactic arm that made the cloud, and so on, all the way to the first moments after the Big Bang. The hand-me-down chain does not break, even at the extremes. If a neutron star is the most extreme rotation we can see while the object is still recognizably matter, the next rung up is what happens when the matter is gone entirely. A black hole is what is left when a massive star runs out of options. Its core was already the densest thing in the universe. When the supernova fails to halt the collapse, gravity wins completely. Matter falls below the event horizon, the boundary from which nothing returns, and what remains in our universe is a region of pure curved space, defined by only 3 numbers. Massachusetts electric charge. Spin. That is all. That is everything we can know about a black hole from the outside. The physicist John Wheeler, in 1973, summarized this with a memorable phrase. He said, "A black hole has no hair," meaning all the messy details of whatever fell in, the colors, the chemistries, The histories, the names, none of it survives. Only the totals. Only the books that have to balance. And one of those three numbers, one of the only things a black hole keeps from its previous life, is its rotation. This is striking when you sit with it. A star, before it collapsed, had a vast amount of structure. Layers of burning gas. Magnetic fields. A history. Convection patterns. Differential rotation, like the sun has. After the collapse, all of that is gone. The black hole has no surface, no atmosphere, no internal layers we can probe. But its angular momentum survives. The mass and the spin make it through the most extreme physical event in the universe and remain measurable from the outside. A spinning black hole is described by a solution to Einstein's equations called the Kerr metric, found by a New Zealand mathematician named Roy Kerr in 1963. Kerr's solution showed something Einstein had not anticipated. A rotating black hole drags space itself around with it. The dragging is real. It is measurable. Physicists call the effect frame dragging, and it means that nothing near a spinning black hole can sit still. Not even space. Even an object that tried to remain at rest, with no force pushing it, would be pulled around the hole simply because the geometry of space is rotating. In April of 2019, a global collaboration of telescopes, called the Event Horizon Telescope, or EHT, released the first direct image of a black hole. The black hole sits at the center of a galaxy called M87, about 55 million light-years from Earth. Its mass is roughly 6.5 billion times the mass of our Sun. The image, when it was unveiled, looked like a fuzzy orange donut, a bright ring of hot gas, surrounding a dark central shadow. That dark center is where space is curved so steeply that even light cannot escape. When astronomers studied the image carefully, they could see something else. The brightness around the ring was not symmetric. One side was brighter than the other. According to general relativity, this asymmetry happens when gas on one side of the black hole is moving toward us, and gas on the other side is moving away. The brightness pattern was the first direct visual evidence that M87's black hole is rotating. Later studies, looking at how the black hole's enormous jet of charged particles wobbles back and forth over an 11-year cycle, confirmed it. The jet itself is being swung around by frame dragging. The whole structure, light years across, is being pulled around because the black hole at its base is dragging space with it. Recent measurements suggest M87's black hole is spinning at roughly 80% of the maximum rate physically allowed. There is a maximum. That is the strange part. A black hole cannot spin faster than a specific limit. If you tried to feed too much angular momentum into a black hole, beyond what physicists call the extremal limit, the event horizon would disappear and the singularity inside would become visible to the outside universe. Penrose showed this would create paradoxes general relativity is not equipped to handle. So nature, somehow, prevents it. The accretion of matter slows down before the limit is reached. Other processes carry the excess spin away. Black holes spin, but they cannot spin past a certain point. And here is the inheritance question, restated for the most extreme objects in the universe. M87's black hole is 6.5 billion solar masses, spinning at most of its allowed maximum. Where did that angular momentum come from? Not from nowhere. It came from billions of years of mergers with other black holes, infall of gas, and the gravitational dance with everything that ever wandered close enough to be eaten. Each event added or subtracted a little. The total at any moment was the running balance of the black hole's life history. Even at the bottom of the deepest gravitational well in the universe, where space curves into a region nothing can return from, the rotation has a story. The story goes back. The story is inherited. The smaller black holes that LIGO and Virgo detect when they merge in the distant universe also have measurable spins. Some are spinning fast, some slow. The distribution is not random. It carries information about how those black holes formed, how they paired up, what kind of stars they used to be. Their spins, before they merged, were already inheritances. Their merger created a new, heavier, still rotating black hole, whose spin is now an inheritance from both parents at once. Even at the edge of physics, the chain holds. Mass merges with mass. Spin merges with spin. The total has to balance. And whatever survives the merger carries the rotation of everything that came before it. We have been climbing the chain in one direction. Now we have to look the other way. If every spinning thing inherited its rotation from something earlier, what is at the bottom of the chain? What did the very first cloud inherit from? This is the hardest question in the field, and the honest answer is that nobody knows for certain. There are theories. They are still being argued over. Let me walk through the leading one, because it is beautiful in its own way. It is called tidal torque theory. The idea was first developed by an American astronomer named James Peebles in 1969, who later won a Nobel Prize for related work on the early universe. The picture is this. In the early universe, just after the Big Bang, matter was spread out almost evenly. Not perfectly. There were small variations from place to place. Tiny ripples, slight overdensities and underdensities. Wherever matter was a little denser than average, gravity was a little stronger. Those denser regions began to pull on each other. And here is the key. Two neighboring regions, both pulling on each other, are usually not perfectly aligned. One is shaped slightly like a long ellipse. The other is shaped differently. The pull between them is not a clean tug. It is a sideways tug, a gravitational nudge that has a twist built into it because of misalignment. That twist is where the first local rotations come from. And it does not violate the conservation rule we talked about earlier, because for every clump of matter that ends up rotating one way, its neighbor ends up rotating the opposite way. The total angular momentum across the pair stays close to zero. The accounting balances. But locally, in each lump, real rotation has now appeared, and once it appears, it gets carried forward. Imagine two slightly stretched lumps of clay floating in space, close enough to feel each other's gravity. They are not perfectly round, so they do not just fall straight at each other. They tug on each other's long edges. They start to rotate, slightly, in opposite senses. The pair has the same total it always had. Each lump, on its own, now has a spin it did not have before. And once that spin exists, it gets passed down to whatever forms inside the lump. So, in tidal torque theory, the first spins were generated, not from some original cosmic push, but from the gravitational dance between neighboring lumps of matter. No center, no external force, just neighbors gently torquing each other into motion as gravity pulled them together. This is the leading theory, and it works well for galaxies that grew up in the standard way. The rotation rates we measure for ordinary spiral galaxies match the predictions of tidal torque theory to within a reasonable margin, but it does not explain everything. Some galaxies rotate faster than tidal torque theory predicts. Some black holes at the centers of galaxies are spinning so close to the maximum allowed by physics that you cannot get them there with neighbor torques alone. Something else has to be feeding angular momentum into the system, and what that something is, we do not yet know. There is also a deeper question. Tidal torque theory generates angular momentum through gravitational interactions, but the small density variations in the early universe, the tiny bumps that gravity amplified into galaxies, those bumps themselves came from somewhere. The current best explanation traces them all the way back to quantum fluctuations during a brief, violent period in the first fraction of a second after the Big Bang, a period called inflation. For most of the 20th century, this was a guess. A beautiful guess, but a guess. There was no direct evidence that the early universe had the small density variations the theory required. The leftover light from the Big Bang, the cosmic microwave background, looked perfectly smooth, embarrassingly smooth. By the late 1980s, several teams had been searching for the predicted variations and finding nothing. Then, in April of 1992, an American physicist named George Smoot stood in front of a room full of journalists and announced that his team had finally seen them. The instrument was a NASA satellite called COBE, the Cosmic Background Explorer. It had been launched in November 1989 into a polar orbit, where it spent years patiently mapping the temperature of the cosmic background radiation across the entire sky. After 3 years of careful averaging, the team had pulled out a signal so faint it had eluded every previous experiment. The temperature of the early universe varied from one place to another by roughly 1 part in 100,000, about 30 millionths of a degree, hotter in some directions than in others. That number, 1 part in 100,000, broke the simple picture and replaced it with a stranger one. The early universe was not perfectly smooth. It had ripples in it. The ripples were exactly the size predicted if they had come from quantum fluctuations during inflation, blown up to cosmic scale during the universe's first split second. Smoot at the press conference said the result was, in his words, like seeing the face of God. It was not a religious claim. It was a stunned scientist trying to describe the moment he realized he was looking at the seeds of every galaxy that would ever form, frozen into the oldest light in the universe. Those seeds are what tidal torque theory grew its rotations from. The lumps of matter in the early universe came from those tiny temperature variations. Those variations came from quantum fluctuations during inflation, which means the spin in your hand right now, the rotation of the galaxy, the rotation of every neutron star in the sky. All of it traces back to random quantum noise in a universe that was less than a trillionth of a second old. That is one of those facts you have to read twice. The reason your atoms rotate the way they do is that the universe, when it was younger than a snap of your fingers, had a small amount of quantum uncertainty in it. The uncertainty became density variations. The density variations became matter clouds. The matter clouds became galaxies. The galaxies became stars. The stars became you. Spin is a fossil. Every rotation in the modern universe is a fossil of those first quantum tremors. Most planets in our solar system rotate in roughly the direction we expect. Their spin axes are tilted a little, but only a little, and they all rotate in the same general sense as the sun. This is what you would predict from a single rotating disk collapsing into a star and a family of planets. Then there is Uranus. Uranus rotates on its side. Its axis of rotation is tilted by about 98 degrees, which is almost a full right angle. If Earth had Uranus's tilt, the North Pole would be roughly where the equator is now, and the entire planet would roll along its orbit instead of spinning upright. There is no good way to inherit this orientation from the original disk. The cloud that became the solar system was rotating in one general direction. All 8 planets, plus most of the moons, all came from that disk, and most of them respect the original rotation. Uranus does not. Something happened to Uranus. The current best theory is a collision. Sometime in the early solar system, when planets were still forming and gravitational chaos was common, Uranus is believed to have been struck by another body, maybe an Earth-sized planet, maybe a series of smaller impacts. Whatever happened, the collision was powerful enough to knock the planet onto its side, and the planet has been rolling that way ever since. We see this exception in many other places. Venus rotates backwards compared to most of the other planets, very slowly, only once every 243 Earth days. The reasons for this are still debated. Tidal interactions with the Sun, possibly combined with the planet's thick atmosphere, may have flipped its rotation over billions of years. Some moons rotate in the wrong direction relative to their planet's spin. Some asteroids tumble in ways that do not match anything around them. Some galaxies have been observed rotating backwards compared to nearby galaxies in the same group. These exceptions are not failures of the inheritance idea. They are confirmations of it. Spin can be exchanged. It can be redirected. It can be flipped. But it cannot be created from nothing. Every time a planet ends up on its side, or a moon spins the wrong way, or an asteroid tumbles strangely, the angular momentum did not come from nowhere. It came from a collision, from a near miss, from tidal forces, from something pushing on something else and trading rotation in the process. Even the rule breakers are following the rule. They just got their hand-me-down from a different source than their neighbors did. For a long time, astronomers assumed that if you added up all the rotations in the universe, the total would be roughly zero. The reasoning was simple. With trillions of galaxies spinning in trillions of different directions, you would expect the random orientations to cancel each other out. There should be no preferred axis. The universe as a whole should not be turning. And for most of the 20th century, every measurement supported that assumption. The cosmic microwave background, the leftover light from the early universe, looked the same in every direction. The distribution of galaxies on large scales looked statistically uniform. There was no obvious sign that the universe was rotating. Then in 2011, a physicist at the University of Michigan named Michael Longo published a quiet little paper in a journal called Physics Letters B. He had spent years with a small team of undergraduate students, going through images from the Sloan Digital Sky Survey. The Sloan Survey is a long-term project that has photographed millions of galaxies in unprecedented detail. Longo's question was simple. He looked at 15,158 spiral galaxies and asked whether they tended to rotate clockwise or counterclockwise from our point of view. If the universe was truly without a preferred direction, the answer should be exactly 50-50. It was not. In the part of the sky toward the North Pole of the Milky Way, there were about 7% more counterclockwise rotating spirals than clockwise ones. The effect extended out to about 600 million light-years. 7% does not sound like much, but Longo calculated that the chance this could be a random fluctuation was roughly 1 in a million. If his result is right, it would mean the universe has a preferred axis of rotation, the whole thing, as one object, spinning very slowly in a particular direction. I want to be careful here because this result is contested. Other groups have looked at similar data and found no preferred direction. A large project called Galaxy Zoo, which used a much bigger sample of galaxies classified by volunteers, reported in 2008 that the distribution of spin directions was consistent with statistical isotropy, meaning no preferred axis, random. So we have a disagreement in the field. One paper says the universe has a faint global rotation. Another says it does not. The question is genuinely open. New surveys, with bigger samples and better automated classification, are still trying to settle it. But sit with what is at stake. If Longo is right, the universe inherited not just trillions of small rotations, but one large rotation, one overall spin that the entire cosmos still carries from before there was a cosmos. Every other rotation we have talked about, the spin of your atoms, the spin of the Earth, the spin of the Sun, would all be small currents inside one enormous slow river, and the river would have a direction. If Longo is wrong, then the universe, taken as a whole, is not turning. The rotations cancel. The river has no overall flow, just small whirlpools scattered everywhere, each one the residue of a local quantum twitch. Either way, the small rotations are real. Either way, every one of them is inherited. The question is only whether the inheritance has a single source, or many. Step back. Take a breath. We have walked from electrons to galaxies, and the same rule has held at every scale. Angular momentum cannot be created or destroyed. It can only be passed on. But why? Why is this the rule? Why can we not, somehow, give a perfectly still object a spin without taking that spin from somewhere else? Why does the universe insist on this strict accounting? The answer to that question came from one of the greatest mathematicians of the 20th century, and almost nobody outside physics has heard of her. Her name was Emmy Noether. She was born in Germany in 1882. By the early 1900s, she had a doctorate in mathematics, but the universities of her time would not give her a faculty position because she was a woman. For years, she taught classes under other professors' names. She worked without pay. She kept publishing papers, year after year, while the academic system pretended she did not exist. In 1915, the great mathematician David Hilbert and Albert Einstein invited her to the University of Göttingen to help them work through a deep problem in general relativity. Einstein's new theory of gravity had a strange feature. It seemed, in some early versions, to violate the conservation of energy. Hilbert and Einstein could not figure out why. They asked Noether to look at the math. She did more than look at it. She produced a theorem that solved the problem and changed physics forever. Noether's theorem says, in plain English, that for every symmetry in the laws of nature, there is a corresponding conservation law. If the laws of physics do not change over time, then energy is conserved. If the laws of physics do not change from place to place, then momentum is conserved. And here is the one we care about. If the laws of physics do not change when you rotate your point of view, then angular momentum is conserved. That is why spin cannot be created or destroyed. It is not a rule somebody decided. It is a consequence of a deeper symmetry. The universe behaves the same whether you face north or face east. That fact, that the laws do not pick a preferred direction, is exactly what forces angular momentum to be passed on instead of being made or unmade. Stop. Sit with that for a moment. The reason the Earth keeps spinning, the reason the galaxy keeps turning, The reason your electrons cannot stop is that the universe, in some fundamental way, does not care which direction is which, and that not caring, that perfect rotational fairness in the laws of physics, is what makes rotation a permanent currency of the cosmos. Emmy Noether published this theorem in 1918. She finally got a paid position at Göttingen in 1923. In 1933, she was forced out of Germany when the Nazis came to power because she was Jewish. She moved to the United States and taught at Bryn Mawr College for the last 2 years of her life. She died in 1935, at 53, from complications of surgery. Most people have never heard her name, but the rule she discovered is the reason every single rotation in the universe behaves the way it does. The reason the moon cannot stop receding. The reason the neutron star in Tarzan 5 cannot slow itself down by an act of will. The reason the spin in your electrons cannot quietly disappear when you fall asleep tonight. There is a deep symmetry in the laws of nature, and that symmetry, like an invisible accountant, keeps angular momentum on the books forever. If you ever wanted to point at a single insight that explains why everything spins, this is it. Not a force, not a beginning, a symmetry, a deep structural fact about the laws of nature, and the work of one woman, sitting at her desk in a country that would not let her have an office. There's a footnote to this story that is too strange to leave out. It comes from another mathematician, working 3 decades after Noether, and it ties the question of spin to one of the deepest mysteries in physics, the mystery of time itself. The mathematician's name was Kurt Gödel. He is best known for a theorem in pure mathematics that proved no system of arithmetic can ever fully prove all of its own truths. But in 1949, Gödel turned his attention to Einstein's general relativity. He and Einstein were close friends at the Institute for Advanced Study in Princeton. They walked home together most afternoons. For Einstein's 70th birthday, Gödel decided to give him a present. The present was a paper. There's a small detail that always stays with me about this. Einstein and Gödel were both refugees in America. Einstein had fled Germany in 1933. The same year, Noether was forced out. Gödel had fled Austria in 1940. They had both come to Princeton. Both ended up at the Institute for Advanced Study, and both had spent decades working on the deepest problems in their respective fields. Their afternoon walks home from the Institute were one of the great intellectual friendships of the 20th century. They talked about politics, philosophy, and physics in equal measure. By 1949, Einstein was 70. Gödel was 43. And the gift Gödel chose was an exploration of the strange consequences of a single feature of Einstein's own theory, rotation. In the paper, Gödel did something nobody had thought to do. He took Einstein's equations of general relativity, the equations that govern gravity and the shape of spacetime, and he asked what would happen if you fed them a universe that was rotating as a whole. The answer was disturbing. In a rotating universe of the kind Gödel described, time itself becomes strange. The rotation drags spacetime around with it, the way a stirred cup of tea drags the cream. And if the rotation is fast enough, the dragging becomes so severe that you can find paths through space that loop back on themselves. Paths that, if you followed them, would let you arrive at a moment in your own past. Time travel, built into the equations, as a consequence of the universe rotating. Einstein was unsettled. He praised the paper publicly, but in private letters he wrote that Gödel's solution disturbed him deeply, because it suggested time might not be the simple forward arrow we think it is. Gödel himself drew a stranger conclusion. He thought his rotating universe was a hint that time, as humans experience it, is an illusion of consciousness, not a feature of physics. Our universe does not appear to rotate fast enough for any of this to actually happen. The closed time paths Gödel described require rotation rates that no observation supports. If the universe is turning at all, the way Longo's data hints, it is turning very slowly indeed. But the paper changed how physicists think about rotation. It revealed a hidden link between the cosmic spin and the nature of time. The faster the universe rotates, the more time gets bent. The more time gets bent, the less it behaves like time. A universe that rotates too much stops being a place where one moment cleanly leads to the next. Maybe the reason our universe has so little net rotation, if any at all, is not an accident. Maybe it is the only kind of universe in which time can work, the only kind in which there can be a yesterday and a tomorrow that stay in their proper order. That would mean the question is not why the universe spins. The question is why it spins so little. And the answer, if Godel was right, is that any universe spinning much faster than ours would not have a future to look forward to. Pull back to where you are, the chair you are sitting in, the room around you, the breath you just took. Inside your chest, your heart is beating. Each cell of your heart is built from atoms. Each atom is built from particles. Each particle is carrying the same fundamental spin that every electron and proton and neutron in the universe carries. The spin in your heart is the spin in the first stars, scattered into the galaxy by their deaths, gathered up by the cloud that became the sun, baked into the atoms that became Earth, woven into the molecules that became you. You are made of inherited rotation. There is no part of you that is still. There never has been. Hold your hand at arm's length. Spread your fingers. Look at the back of your hand. Every cell has dozens of small rotating things inside it. Every one of those rotations is part of a chain that goes back almost 14 billion years, with no break, no first push, no original start. You did not gain that rotation. You borrowed it from the atoms in your food, which got it from the soil, which got it from the rocks, which got it from the dust cloud that formed the planet, which got it from the larger cloud that formed the sun, which got it from the spiral arm of the galaxy, which got it from the proto-galactic cloud, which got it from the slow gravitational dance of the early universe, which got it, ultimately, from the quantum trembling of inflation. You will give it back. When you breathe out, some of those rotations leave your body, attached to atoms that drift into the air. When you eat, you take in new ones. The flow never stops. You are a place where rotation pauses for a few decades on its way to somewhere else. The cosmos is doing this with every body, every plant, every cloud, every star, every galaxy. The same currency, passed from hand to hand, and never created or destroyed. And it is happening underneath you, too, in a way you may not have known about. 3,000 miles below the chair you are sitting in, deep in the center of the planet, there is a solid ball of iron and nickel about the size of the moon. It is so hot that, at the surface, it would vaporize instantly. The pressure at that depth is so high that the iron stays solid anyway. We cannot see it. We cannot reach it. But we know it is there because seismic waves from earthquakes pass through it differently than they pass through anything else. And the patterns reveal a solid core nested inside a liquid one. That iron core is rotating, not at the same speed as the surface you are sitting on. In 1996, two seismologists at Columbia University, Xiaodong Song and Paul Richards, used decades of seismic data to show that the inner core was rotating slightly faster than the rest of the planet, about 1 extra degree of longitude per year. Slow but consistent. They called it inner core superrotation. The implication was strange. Underneath your feet, a moon-sized iron ball was spinning ahead of the surface, like a small inner planet running on its own clock. Then, in 2024, a team at the University of Southern California found something stranger still. Looking at 20 more years of seismic data, they discovered that since around 2010, the inner core has been slowing down. It is no longer racing ahead. It is actually moving slightly slower than the surface now. The first time this has been measured in roughly 40 years. The core is backtracking, retracing some of the path it had pulled ahead on. We do not yet know why. The leading guesses involve magnetic forces from the liquid outer core and gravitational tugs from the dense rocks of the mantle. But the picture is not settled. Whatever you are sitting on right now is, in this very specific way, not one rotation but several. The crust under your chair turns at one rate. The mantle below the crust turns at almost the same rate. The molten outer core flows at its own complicated pattern. And the solid inner core, the deepest part of you, the part that is closer to the center of the Earth than to anything else, has its own clock. A clock that has been speeding up and slowing down on timescales we are only beginning to measure. The planet you live on is not a single spin. It is a small set of nested spins, each one slightly different from the others, the whole thing gradually shifting decade by decade. There is something quietly comforting about this. You did not have to start your spin. The universe handed it to you, on the day you were assembled, with no fanfare and no return policy. You are not responsible for keeping it going. It will keep going on its own. The rule that protects it, the symmetry Noether found, is older than you, older than Earth, older than the first stars. It will outlast everything. When the last star dies, the rotations will still be there. Slower, perhaps. Spread thinner. But there. The black holes that survive will keep their spins for unimaginable lengths of time. The atoms that drift through the empty future universe, if any are still bound, will still carry their fundamental quantum spin. The hand-me-down chain does not end with us. It does not end with stars. It may not end at all. There is one more thing to say, and it is the strangest of all. We have treated rotation as a property of objects. Things rotate. Particles rotate. Galaxies rotate. The rotation lives in the things. But there is a serious idea in modern physics that turns this picture upside down. The idea is that rotation might not live in objects at all. The objects, perhaps, live in rotation. It comes from a field called loop quantum gravity, which is one of the leading attempts to combine Einstein's relativity with the quantum mechanics of small particles. In loop quantum gravity, space itself is not a smooth, empty background. Space is built out of tiny structures called spin networks. The structures are made of lines that meet at points, and at every point, the lines carry a value that is, mathematically, a quantum spin. Space, in this picture, is woven from spin. Not space that contains spinning things. Space that is itself made of rotational quantities at every point. In that picture, the question of why everything spins gets a strange new answer. Things spin because the fabric they are made of is, at the deepest level, rotational. Asking why things rotate would be a little like asking why things take up space. I want to be careful here. Loop quantum gravity is unconfirmed. It has not been tested. We do not have the experiments to look at space at the scales where its structure would matter. The theory may turn out to be wrong. Other approaches, like string theory, paint different pictures of what space is made of at its smallest scales. So treat what follows as a beautiful possibility, not a settled fact. If loop quantum gravity is right, the reason there is no first push, no original moment when rotation started, is that rotation was never started because rotation is part of what space is. As a metaphor only, you could say the universe is not a stage on which spinning things move. It is a fabric that has rotation woven into it. In that picture, the strangeness of where we started this conversation resolves itself. Of course, rotation is everywhere. If rotation is part of what reality is built from at the bottom, you are not a thing that is spinning. You are, possibly, a knot in a much larger pattern, and the larger pattern, all the way down, may be rotational at its core. Tonight we walked from the electron in your hand to the possibility that space itself is made of rotation. We met a 1922 experiment that proved the wrong theory and got the right answer. We met a sun that rotates at different speeds at different latitudes, and a moon that is leaving us at the speed our fingernails grow. We met an ice skater whose pull-in trick is the same trick a collapsing star uses to spin itself up to nearly the speed of light. We met a black hole 6.5 billion times the mass of our sun, dragging space around with it as it turns. We met a planet on its side, a galaxy that may have a preferred direction, an iron core under our feet whose rotation is mysteriously changing, and a mathematician who built a universe where time eats itself. We met Emmy Noether, who explained why all of this hangs together at all. And we met the possibility that the question itself was wrong. That rotation is not something things have. That rotation is something things are. I do not have a clean ending for this. The science does not have a clean ending. Tidal torque theory explains some of it, not all. Galaxy spin asymmetry results are contested. Loop quantum gravity is unverified. The motion of the Earth's inner core is being argued over right now in current journals. The original source of the inheritance, the first quantum twitch in inflation, is still beyond our reach. But here's what I keep coming back to. Of all the things the universe could have been, it could have been still. There's no obvious reason it had to come out of the Big Bang with rotation in it. A perfectly symmetric explosion, expanding outward in every direction, would not have needed any spin at all. And yet, almost everywhere we point our instruments, at almost every scale we can measure, we find rotation appearing. Particles, planets, stars, galaxies, black holes, even the iron beneath our feet. The pattern is too consistent to ignore. The universe, as far as we can tell, is not a still place. The stillness we feel sitting in a quiet room is a local illusion, a small pause in a vast ongoing motion that runs through almost every atom in our bodies and almost every galaxy we can see. That motion is borrowed. It will be returned. Nothing about you is original, and nothing about you is final. You are a moment of organized rotation, briefly held in the shape of a person, on a planet that is itself a brief shape, in a galaxy that is itself a brief shape, in a universe that has been quietly turning since before turning had a name. If this kind of slow walk through deep science is something you want more of, subscribing quietly helps the channel continue. And I am grateful you spent this night here. Now let your eyes close. If they have not already, let your shoulders drop. Outside your window, the earth is turning. 3,000 miles beneath your feet. The iron core is on its own slow clock. Above your roof, the sun is sweeping along its orbit. Around the sun, the galaxy is rotating. And inside the chair you are in, every atom is doing what atoms have always done, what they have done since before there were atoms. Spinning. Inherited. Quiet. Continuous. Good night.